All right, so today I want to present you, as you see on the screen, machine learning on mobile with Firebase. So if I may, a little bit about myself. So I started with artificial intelligence and machine learning during university. And as my main being Android developer, naturally, I wanted to see how I can bring machine learning to mobile. So I'm curious, has any one of you worked with machine learning or read a little bit about neural networks and so on?
Yeah, bits in the university as well.
Awesome, great. And I guess you notice how much we can do with it. I know right now everything is about large language models and how we can build with those kind of tools. But machine learning itself allows us to process and to work with really specific things. And this is amazing for mobile because our phones are really, really amazing devices. They have a lot of sensors and a lot of ways to gather information from the outside world. And that information we can process and we can do really, really cool things with it. All right. So let me present you a little bit our agenda for this presentation. So at first, I want to make an introduction and give you a context about the machine learning world in mobile. Then talk a little bit about the state of it and how it's implemented. Then I want to give you an overview and capabilities of the Firebase machine learning kit. Then how we can work with custom models, because in the end, we want to bring our own work to our application. Then I want to showcase a demo. It's a little project, a little application that to build. It's a car model detector application. And through this application, we can see how easy it is to integrate the Firebase machine learning capabilities into our project. I will showcase both the custom model that I worked with, and I will showcase the object detection predefined functions that Firebase ML offers, as well as an integration of Gemini 2.5 API. Also, in the end, I want to take a look at legal and privacy considerations and talk a little bit about GDPR or CCPA and best practices about how we should handle user data with machine learning. Also, we can take a look about the future of AI in mobile, and at the end, have a Q&A, and I hope a really productive discussion. Also, you can ask any question during the presentation. So please, if you have any questions, stop me and let's discuss. But of course, at the end, we have this large Q&A session. Good. So moving on the introduction and context and see why AI matters for Android desktop. So as I mentioned, there are recent breakthroughs in large language models and generative AI, and those are in the spotlight, like ChatGPT, Gemini, Claude, and so on. But neural models can be trained for very specific problems, like recognizing a certain object in a camera field, detecting anomalies in sensor data, translating text in real time, classifying domain-specific images or sounds. So with this kind of abilities, we can do really custom applications. These are made possible on Android by things like Neural Networks API or NN API, and the TensorFlow framework. The Neural Networks API, as of now, it is deprecated, and Google is actually going towards the TensorFlow integration. So I recommend you focusing more on that, but it's good to know about the baseline that it was built upon. This is deprecated as of Android 15, but to meet these needs to progress in the machine learning field, Google developed this TensorFlow Lite Play services, and it's provided at runtime for custom on-device ML models. As I mentioned in the introduction, I want to point out the responsibility when working with machine learning and especially data. So it is both a technical challenge and an ethical and legal one, because if we process user data, we will need to be careful about this data and how we process it. As well, what tools we use to process this data, because if we use Google's API or other APIs to process this data, we are also liable for how they process this data. And we need to present and be transparent about how the user data is used. So with AI, data is basically the fuel, and handling carelessly can lead to privacy violations and compliance risks. So we need to be really thoughtful about that. But what is the state of AI in mobile apps? Well, we can have multiple, well, 3 approaches. One would be on-device AI and machine learning, cloud-based one, and a combination of both. So on-device has really, really nice strength, like having low latency. It works totally offline. We can have sensitive data on the device and handle it locally, or have real-time use cases. But this is really, really challenging because it's limited by the device hardware. It is limited by the model size and complexity restrictions of the neural model. What I mean by this is that being on a mobile device with limited, even though right now our mobile devices are really, really powerful, they are still limited compared to the cloud resources in terms of processing power. So this would be a big challenge to have a model and run it on the device. We have the cloud-based approach, which allows us to call APIs and have all this processing power of the cloud infrastructure. This gives us access to larger and more complex models. It's a lot easier to integrate, improve, update, and gives this our possibility to scale. And sure, it can run resource-intensive computation. We can upload a large amount of data, but to have these kind of possibilities, we will require financial resources, basically. So the cloud-based approach, of course, doesn't come without challenges. Also, this will require internet access. So if we want to focus on a local approach for our application, and we don't want to connect to the internet, using cloud resources will be a challenge. Of course, there are also privacy concerns, as I mentioned in the slide before. By providing this data to a cloud provider for the machine learning models, we will hand over this data. So we need to be careful and what to see and check what are the policies and make this transparent to the user. And in the end, the best approach to have a great product, a great application, would be basically to combine these two and focus on what's important for the user data, what's important for the security, and move all that locally and use a on-device approach. While if we need more power and we are sure that we can safely handle the data, we can use the cloud infrastructure for our needs. One really good example for this is Google Photos. Like they, as you maybe know, and used Google Photos, they have those face recognition collections that they make, and this runs on device. It also can make photo classification, but also it can run complex search queries or generative edits and those powerful models that can help you enhance your photos, which run on the cloud. So that needs internet connection, that needs uploading your data to the cloud. but it offers you really, really powerful tools. So 3 ways we can approach machine learning on the cloud. And now the question is where Firebase fits in here. So Firebase Machine Learning Kit is positioned to help Android developers leverage AI really fast by providing a ready-to-use on-device model, offering cloud-based APIs for more advanced tasks, allowing custom model hosting. As I will show in the demo, we can upload our own model to solve a particular problem. And we basically can train and use our own data for this custom model. So the fact that Firebase allows us to use our model and have it downloaded locally, which you will see in a moment, is amazing. We can focus on the on-device approach. But also Firebase allows us to go over on the cloud approach and offers us a lot of great tools and great powerful tools by just calling an API. They also offer ways to train our models on the cloud infrastructure and allows us to upload our data and use that data to enhance our models. But that is, of course, cost-based, and it uses the cloud infrastructure. So we need to add this data to the cloud, which comes with the drawbacks I presented. Also, another really great thing about Firebase is that most of us, let's be honest, are pretty used to Firebase, and we use a lot of really cool features like remote config, analytics, and different security rules. And these are really, really nicely integrated with the machine learning feature that they have. So we will use a familiar environment with really, really powerful tools to integrate our neural models. And let's see about a couple of capabilities that Firebase has. So Firebase allows us to, as I said, have some already provided features. They have small models do different quick things like object detection and image labeling, text recognition, face detection, translation, landmarks recognition, barcode scanning. All of these are parts of the Firebase machine learning kit. And these models are on-device models, which means you don't need to send any data to the cloud in order to run these models. Of course, these models are limited in their power capabilities, but they have also, depending on the model, they have the possibility to use the cloud models to run more demanding tasks. But overall, this is a great plethora of models that can help us develop really, really cool apps, like using barcode scanning to catalog stuff, or use text recognition for image processing, object detection, so we can crop out different objects and also label them. This is an amazing research that we can use. Also, these don't require training. As I said, these are already provided models. So this will be just get them from the cloud. They will be downloaded on device and then they will be used. They are based on TensorFlow and they will work basically natively in our application. And they are really, really well optimized for Android. Now that I mentioned multiple ways to use predefined models, we can upload our custom model to Firebase. Now, if you already read or worked with neural models, you know that there are multiple ways you can develop. Of course, we mostly develop in Python here, and we use different frameworks. One popular framework is, of course, TensorFlow. Another one is PyTorch. I myself am more familiar with using PyTorch, and I use more during university time PyTorch. And Firebase being based on TensorFlow, we cannot upload directly PyTorch, but we have a solution for this. We can map our models to TensorFlow. The only caveat is that Firebase custom models provided through the machine learning feature that we use on our application uses TensorFlow Lite models. TensorFlow Lite models are not full-fledged TensorFlow models, which means they are quantized, making them lighter and more easy to work on the mobile architecture. So they will run more smoothly and faster on mobile. This means that either some parts of our models may not be available on TensorFlow Lite, or they will be limited in power. So this is something that we need to take into account when developing a custom model and wanting to apply it to the application. Also, on some other limitations on Firebase side, the model itself, the file of the model cannot be larger than 100 megabytes. And also, as I mentioned, not all TensorFlow operations are supported. So this custom model works really similar to the predefined models that I presented in the slide before. It will download the TensorFlow model from Firebase on the device, and it will use it locally. So no data will leave the application. This is, again, amazing because we can go with the on-device approach. We can also provide this TensorFlow model directly on the device. So we can add it as an asset to our application and just provide the URI to this asset and load it into the, it's called interpreter, the interpreter that runs the model on the application. So if we don't want to connect to the internet at all, so we can get the model, we can just upload it as an asset in our application. Of course, Gemini 2.5, this is a really, really great tool, and it's available as an API to our applications. If you take a look on the right side on the flow that a short flow that I presented, basically in the demo application that I will show you, we have an image of a car, for example, and we get the recognition for it. So we know the brand of the car. We can send this brand to Gemini. We can define a prompt for Gemini and get some text from it and use it in our application. In my case, I use the text for giving a description and recommendation on whether the user should buy or not this car and what are the most popular versions of the car. But of course, you can do anything basically with this. Moreover, we can define really intelligent prompts that can give us, let's say, schemas for the answers from Gemini and try to process data in this way. Then we can define some way to map the schema and then use this data in our application as a class, for example. So this is a really, really powerful tool. It's available directly through an API, and it integrates really, really well with the other Firebase tools. Now, Gemini is not directly part of Firebase machine learning, and moreover, Gemini runs completely on cloud, so no on-device capabilities here. So you will need to send data to Gemini in the cloud. But it is really, really powerful and can give us a lot of options. Also, besides text processing, the Gemini API is capable of processing images directly. Now, this is also a predefined option and a predefined feature, meaning that you will process the image the way you are already used with large language models and how they process these images. But my recommendation is if you want to target some kind of functionality on the device, and we want to process, let's say, images or even other data like the accelerometer on the device or other sensors. It's better to have your own custom model. Sure, it takes time to train, it takes time to gather data, but that way we can tailor our application exactly to the needs of the user. But sure, we can use really generic tools like Gemini to enhance the experience. Now, a little bit on the pricing model, because you definitely are curious about this. This is all great, all amazing tools that we have, but they come at a cost. So the great part is that from development perspective, everything is free in some limits. So we can test and explore the functionalities really, really easily. And after we want to go up and start using them on a large scale, basically the cost is per usage. So the more it's used, the more it costs. Why I want to highlight this is because we need to be really, really careful and really smart on how we develop the application in order to minimize the calls we make to the API, to minimize the data we send, and be smart on how we handle this in order to reduce our cost on our application. Good. We can move on with working with the custom models. Here in this section, I want to show you the model I used for this particular demo and a little bit about the story behind it. So for those who are not familiar to the neural networks, you can think about neural networks just like a black box. It's a black box that does some function. And these neural networks take some input and then they map it to some desired output. In the case of car classification, we want to take an image of a car, and that image we need to have a label assigned to it. This means we will get a, let's say, 3-channel image, like RGB image, with different pixel data. That pixel data we want to pass through our neural network and receive a result, let's say a number between, in my case, it was 0 and 48 because I had 48 brands of cars. And my model will output one of these numbers. Or better said, it will output probabilities on which of these numbers, of these brands of cars, is more probable to be in that image. And the architecture is called the ResNet. This is a little bit more older than the current transformers that I used the large language models, but it's a really, really great tool for image classification and image processing. It's called ResNet because it uses something called residual connections. This is because one of the big problems of neural networks is if you want them to be really, really powerful, you need to make them really, really large. And if you make them large, information can get lost in the process of getting from the input to the output. So these residual connections just refresh the connections, as you can see on these lines, and make the network more powerful. So ResNet architecture, if you want to read about it, it's really, really great for image analysis. And it was really, really nice for this demo. Initially, the model that I trained was also cropping the car out of the image and then make the input only on the car. If you want to check out, it's called YOLO. It comes from You Only Look Once. It's another kind of neural network that crops things out of the images and also labels them. But just for now, this kind of model is really good for image analysis. Now, I made this I trained and defined this model in PyTorch. So this is a really cool example, and because it showcases that it doesn't matter what tools we use. We can map them to TensorFlow, and by mapping them to TensorFlow, we can use it. So what I did here and what I want to showcase here is that through, let's say, 37, 40 lines of code, we can define our inputs, our model, and then transform it to TensorFlow. It's a little bit cumbersome, but it gets the job done. So it's not a problem if you choose another environment to develop. You can use it in Firebase. It uses, of course, the PyTorch library to develop the model in PyTorch. This is TensorFlow library and also ONNX library from in Python to map our model to TensorFlow. Then after mapping it to TensorFlow, it maps it to TensorFlow Lite. So it will compress basically the model, making it smaller and more available for the mobile environment, and also it will make it run faster on the tools. Let me go to the other slide so I can actually show you how this quantization basically works, and it may work in different ways. We can change the variable types that we use. For example, we can go from a float 64 to a float 32, or from 32 to 16, and this way we make some quantization. We make our variables smaller from size perspective. We can also strip down different connections in our neural model. So our neural model has millions of connections, but we can just turn some of them off, or make the neural model with less neurons, for example, so less connections in it. This way, we make the model small enough to run properly on mobile devices. So this is one of the limitations of TensorFlow Lite. Other limitations are that they need to be small in size, as I mentioned, under 100 megabytes to be able to upload them on Firebase and to make them work properly on the device. This quantization, while it's great for making the model smaller, will in fact make also the model less performant, unfortunately. Of course, because you have less neuron, you have less connections, you have less precision in your variables, this will make the prediction less performant. So we need to balance how much we can strip down from the model to make it work. Why not? Let's jump into the card demo and see how easily it is to integrate all of the things that I just presented. I know I talk a lot, I showcased a lot of things, so are there any questions before going into the card demo? Right? If not, let's go. Okay. Going on to Android. Good. All right. So what I have here is really short application made with Compose. What I want to basically showcase of this application is that we can basically define use cases and configure our repositories using the repository pattern in such a way that we can really go towards that black box approach of neural models. So basically, we can configure what we want in the input, then we can configure the neural models, and then run the recognition, and then receive this this prediction that we can use in our application. Good. So a little bit about the application is basically it has a single activity, it has a couple of composables, it has a home screen, as you can see here. This is the home screen. It allows us to choose what model we want to use. I have two examples. One example is the custom model that I added, and the other example is the predefined object detector. This will compute the bounding boxes of image of objects that it recognizes in the image. For now, let's keep it on custom model. We have a home screen, we will have a prediction screen, and that's basically it. I will use for this demo the in-camera of the emulator. I have some images prepared for the presentation. I will add these images to the emulator so we can see them on the camera. I already have a hammer car here, which we will be able to see and run the recognition on. But before doing that, let's check a little bit how the flow goes. So basically, we will have the image here. Let me go to the image itself. Now, this image is an image part of the dataset that they use to train the model. Okay, so now we have it on the screen. It doesn't need to be perfect. Basically, we want the model to see. We want to see what the model recognizes. And here in the view model, I just added the use cases. One of the use cases, this image classifier use case, this is the use case that uses the custom model that I made in order to classify this image. Now, in short, what we will be doing here, we will use the camera in Compose to get the image. I will store the image on the device memory and I will get the URI to it. I will load this bitmap from the URI and have the bitmap as a bitmap object to process. Before feeding this bitmap to the model, first we need to pre-process it. So let me show you a little bit about what we need to do on processing. So the bitmap itself has its own way of holding data. But for the recognition to work, we need to feed a byte buffer of our image to the model. So we need to process this bitmap into a buffer that holds the data for the red channel, then the data for the green channel, and then the data for the blue channel. And in order to do this, we need to define a couple of things. We need to define the size of a flow first. So this will be the float size. One second. Okay, so the float variable size divided by the byte size, because we want to go bit by bit. Good. Then we want to define how large the buffer of the image is. So for this, we need to allocate the size. So the size will be float size. We use float size because each pixel value will be a float here. Multiplied by 3, multiplied by 224, and again 224. What this means? 3 is the number of channels, red, green, blue. 224 is the size of the image, the height and the width that we want to feed the model with. Models have fixed size. Of course, there are other smart models that use variable sizes, but my model uses an input of 224 by 224. So that's why we want to define this buffer. Then what we need to do is to parse the image itself. So we want to go column by column, row by row, and define the pixel value and put it into our input buffer. Because I know it's a little bit late, I will just bring this in directly. And we can go over the code itself. So we need to go pixel by pixel in the bitmap. As you can see here, I have the scale bitmap. This is because our bitmap will not be 224 by 224. So we need to first scale it to 224. Now, of course, this will skew the image, but during processing of the during the training of the model, depending on how you apply the transformations to the image, you'll do such transformation to the image either way. And the model should know how to handle this kind of transformations and be tailored already to such kind of transformation. So there is not a problem that we scale the image like this. All right, and then what we do is basically we go pixel by pixel, X and Y through the bitmap. We get the value for this in red, green, and blue. Then we want to normalize the values. This is also a remnant from the training process of neural networks. We want to scale it in the values that we use during training. During training, I use values between 0 and 1. And we want to normalize these values to 0 and 1. And then for this, I will just divide by 255 because the bytes are from 0 to 256. So we can get this scale. And then we can put this into the buffer. Then we fix this import. Good. Now we have the pre-processing method. Here we can go crazy on how we want to pre-process our image. It depends on the training process. It depends on what we want to achieve. If you have a huge image and you just want to crop something out of the image, you can add the cropping here. We can do this pre-processing on the bitmap before converting it to a byte buffer. But for the demo purpose, we want just to convert it to a buffer so we can feed it to the model itself. All right, then let's go to the classify image method that I defined in the classifier repository so we can see how we can define the components from Firebase actually that will allow us to use this byte buffer. Okay, so for this, we will need to define a interpreter. This interpreter is the object that will get the buffer and run the recognition. So let's define this. The interpreter is part of the TensorFlow library. Of course, in order to have all these tools, you need the TensorFlow implementation. We need the Firebase machine learning implementation. I can show this at the end. Good. And we want to initialize this interpreter. In order to initialize the interpreter, we need a couple of variables and conditions. So first, let's start with conditions. We have these custom model conditions, download conditions that we can apply. And we have a builder for theme. Now, we can require Wi-Fi, we can leave the download happen on data as well. It's just how we want to approach the download. And for now, just call build. We should have more options here just to make sure that the download goes through and we don't have any issues with the model. Since the models are not that large, but reasonably large, like 5100 megabytes, just to make sure it downloads properly. Good. And in order to get the model from the cloud, you will use the Firebase model downloader. And then call get home. Now, for the model, we need to provide our model name. My model is called car detector. I can show you it here. So of course, we need to work in tandem with the Firebase console. In the Firebase console, we find all the machine learning tools under the machine learning item. Here are the predefined models that Firebase provides us on device, and of course, with possibility to use cloud models. And here in the custom tab, we can upload our own model. To upload the model is just add the model and provide the file to Firebase. After, of course, after converting it to TensorFlow Lite. Our model is called car detector, so we just provide a name here. Then we need to define a download type. Okay. And for now, we will use local model update in background, so it almost in the background. And pass the conditions to the model. Then we can add a success listener to this. And the success listener will provide us with the model. Once we have the model, basically we have the model file. So we can access this file and put it into the interpreter. I will show you after finishing this where exactly it's downloaded. If we want, we can actually log this so we can see the file itself. And let's define the interpreter based on this model. Just by passing the model file. So it will read the model from the file and assign it to the interpreter. Good. Okay. And let me also add another wait here, just to wait for this to finish. Good. Now let's add the classifying logic. Just to make sure that our interpreter is, if our interpreter is null, then we should initialize it. Let's add a mode failure result. All right. And now let's use our buffer to run the recognition. So since our input is a buffer, of course, our output will also be a buffer. So we need a buffer size. The buffer size of the output will actually be 48 times the float size, because we will have 48 floats at the output, which are the probability of that brand to be recognized. So for this, we want to multiply 48 with the float size divided by the brand size. And this will be used to define the model output. So, arrow. Now we define how we want our output to look like. We have our input, we have our output. All we need to do is to use the interpreter to run the recognition. For this, we just call run. We get the byte buffer from our bitmap. And the model output that we want to put our data in. Then we want to return this result as a success. So model output. And we want to map this output because this output is actually in as a byte buffer. So we want to actually have a class prediction. Let me actually.
Dragos, we have one question.
Yes, please.
Yeah, actually, not a question. We have 5 minutes left. Like maybe we can speed up with the code. Maybe you can share more details after.
Sure. It's just I want to finish after using this, showcasing this, showing it how it works on the device, and then be done. What else I can show you or wanted to show you is actually that after running the recognition here, the model file will actually be downloaded on the device storage. So we can see it directly in the Firebase demo files. We will be able to see it directly here in the files of the device. And the same thing we can do with assets. So we can store it basically wherever it suits us. We can store the model on the device storage and have the URI to that file. Define the interpreter based on that file and just use it basically. So we can work completely on device with the model. Yeah, I see there are 5 minutes left. I don't think we can go on and finish this, but the main idea is that we have an input our input for this demo is the image. This input must be converted to the proper format that the interpreter wants, which is a byte buffer. Basically, we need to want to parse our bitmap and make it as a buffer. And if we want to apply any other transformations or any other processing on the bitmap before feeding it to the recognizer, we can do that. After, we need to define how our output we want to look like. And this basically depends on the model we use. And then run the recognition. The recognition will fill in the buffer with the data. Then we need to convert this buffer to some meaningful output. In my case, it would have been a int number between 0 and 48. And based on this number, I would map it to a car brand, for example. And just like that, we can add a really, really powerful feature, a really, really powerful function to our application and just use it as an use case. All right, since we don't have that much time, let me go back to the presentation. And just in short about how we handle user data, and one example I want to give you is that the fact that we allow the user to take pictures and send these pictures over to process them. So we process them on device. This means that no data will leave our device. But for example, if we will send this image to Gemini, for example, that means we are liable of how Gemini will process this image. And we want to make sure we inform the user that this is happening to the image the user uploads. So the fact that the user can take any kind of image, even though our purpose is for the user to take images of a car, they can take an image of themselves, and that's personal data, basically. So we need to be really careful on how we handle the data and if the data can be linked to the user. So I know it was a lot, but if you have any additional questions, please feel free to ask. If not, you can also message me and I can answer them asynchronous. I will be really happy for it.
I didn't get to from where you're downloading this model.
So the model is uploaded directly in the machine learning option here on the custom part of machine learning. And here we can upload directly the model. We need to give it a name. Then we need to import a file. So the file is a PDF file, if I'm not mistaken. So go back to the presentation. And here. So it will be output. The output will be a TensorFlow Lite file type. And this file, after you convert it to this kind of file, even though if you have a TensorFlow model, you need to convert it to TensorFlow Lite. So you need to have this conversion to TF Lite file. You need to upload this TF file here. And after you upload it here, you will have a unique name for it. And you will be using this unique name to get it with using the Firebase model downloader.
You try to update the model. I mean, imagine you release the first version and then the second you just want to replace the model, not the raw app.
Yes, so as soon as you want to access the downloader, it will check whether there are a new version for it. So it will update it. Basically, you need to define a flow to update the file itself and use the new file. But if you change it, the Firebase model downloader will make sure that it will be updated.
Could you go back on this previous script? How often you need to update it? This
you don't need to update it. By what do you mean by often?
This previous script that you had in another screen.
Okay,
Not
okay.
an
This
not,
one.
Yep.
So this script, you need to run it only once your model is ready. Of course, if you do any changes to your model, or if you run some more sessions of training, you'll need to convert the model again. Basically, what the script does is it takes the model file. It doesn't matter how you store it. If you might have some preferences. For example, you can store it in a .pkl file, and you can read it as a torch model, for example. This is what I did. So I loaded the model here with model. I defined the model itself, and then I loaded the dictionary data from the file I stored it in. And now this model variable is my model in Python. I define basically how it looks like, how the input look like, and some other configurations that I want to do for the export. And the Onyx library will convert my PyTorch model into a TensorFlow model. And this is what this part of the script does. And as soon as I get the TensorFlow model, I can convert it to TensorFlow Lite and just store it in TensorFlow Lite. So you can imagine you need to do this operation only once, basically, once you have the model done.
Okay. Do you have any pet project to play with, or something you can share as a resources?
Yes, definitely. I can share the repository to this card demo.
Cool. Thank you.
Thank you as well.